Right. Today we're going to be discussing sources of drinking water. We're going to cover the hydrologic cycle, surface water, groundwater, and then emergency and alternative sources of water. So I'm sure some of you are familiar with the hydrologic cycle. It's what takes water and takes it from the earth, brings it up into the atmosphere, and then returns it to the earth through precipitation. Right. So what is the hydrologic cycle? Well, it's the constant movement of water from the surface of the earth to the atmosphere and then back again. So the major steps of the hydrologic cycle is that water will move from the earth to the sky through evaporation and transpiration. Evaporation is the water that evaporates or turns into a vapor and then returns to the atmosphere. And then transpiration is what takes place on vegetation. So when you see your vegetation go from green to brown, that is the process of transpiration. Water vapor will form tiny droplets known as condensation. Once you have enough condensation, that will turn into precipitation in the form of rain. So once some water falls, it'll hit the trees and the vegetation, and that is a process called interception. And then the rest of it will fall to the earth and penetrate the ground or turn into runoff and recharge surface waters. Um, and yeah, some of the terms you're going to want to know is for the hydrologic cycle is evaporation, which is the surface water becoming a vapor. Transpiration, like I said before, is where water vapor lost to the atmosphere from living plants. And then you have evapotranspiration, and that is just the sum of both evaporation and transpiration. Next, you have condensation. The water changes from vapor state to a liquid state. Precipitation, again, that's where it collects enough and then falls to the earth. And then percolation, where the water is seeping through the ground. You have different types of sources for surface water. In California, we have multiple sources of water. Um, As you can see up here, just northeast of the Bay Area, you've got what's known as the Delta. And just south of that, you have what's called the State Water Project, or the SWP, which takes water all the way from up there and brings it us down to us down here in Southern California. Another is the Angeles Aqueduct, which is coming from the Mountains and bringing that water down to the Metropolitan Water District. And then it is sent on further down if it's not consumed there. Then you have the Colorado River Aqueduct that is bringing water from the Colorado River all the way into the Metropolitan Water District system and then sent on down to us down here in Southern California. You do have some local groundwater and water recycling and conservation efforts that happen down here. So, what is a surface water? As well, it's all water open to the atmosphere and subject to the surface of or to surface runoff. Most large population centers must be served from surface water sources. Just it's the fastest way to move large amounts of water, and when you have large populations, that is the only way to get water to them in an efficient manner. So, when a city continues to grow in spite of insufficient groundwater or surface water availability to supply the public and industrial needs, it's necessary to reroute surface water through the city or to the city from other areas through canals and pipelines. So, the water characteristics of surface water would be defined as a variable composition. As water is used for runoff, it's collecting anything and everything that was on the surface of the ground and taking that to a water source. You're typically going to have a low mineral content, but you'll have high turbidity and color, like I said, as it's collecting everything as it travels to the water source. You're going to have a very high dissolved oxygen rate as it's, at the surface of the water mixing with the atmosphere. likely you're going to have poor taste and odor issues. Again, you never know what it's collected on its way to the water source or lake, reservoir, what have you. Uh, so typically, this is going to be the source, though, for what we call an urban source of water, SOW, source of water. And then it is assumed, you should assume that every source water that you can see is contaminated, as all kinds of wildlife, discharges, everything kind of winds up in those. Again, in the taste and odors are likely going to be organic. So, what are the constituents of rain and snow? Well, it is the source for most surface water supplies. However, it does collect dust and other suspended solids in the air and dissolved gases. Um, if you've ever gone outside and looked around after a heavy rain or something, you notice that the air is just much more cleaner, and that's exactly what just happened. The rain has connected with the dissolved particles or suspended particles floating through the air and taken them to the ground. And that's a process known as atmospheric deposition. So it's just a way of cleaning the air, only for a short time. So sometimes they are collecting natural deposits, such as from forest fires, volcanoes, and oceanic salt. And that's what it's collecting. And then the rest of the time, it's collecting it from human activities, such as industrial processes, combustion, and motor vehicles, etc. So rain and snow, without the impact of human activities, is very soft, low in total solids and alkalinity. It has a pH slightly below neutral, so that would make it more acidic. But it is quite corrosive to metals, obviously. Anytime you've probably noticed that, any vehicle in areas where it snows, the undercarriage is typically rusted, and that's because of the corrosive characteristics of that water. So, when it does rain, you have what's known as runoff, and this is water that does not infiltrate into the soil. It travels over the land and to a surface water body. The characteristics of that water are going to reflect both the surface characteristics that it's traveled over, and which is typically the geology of the area. So when you find areas that have more soluble formations, such as gypsum, rock salt, and limestone, it's going to carry those through, and it's going to have more of an effect on the chemical characteristics of the surface water. So the less soluble formations, the composition will be more like that of rain. Water flowing over decomposing organic matter will increase the carbon dioxide levels, thus increasing the amount of mineral matter, and dissolved by the water. So surface runoff is going to have a highly variable characteristics to its water quality, depending on the natural conditions that it is flowing over or any human influences that have taken place. Long retention times can be good for the water quality. It slows down the flows, recharges the groundwater, aquifers, and there's less erosion and less flooding in those areas. The longer the contact with the soil means obviously the greater in the mineral contact. Fast moving water will have the opposite effect, increased erosion, less mineral content. But water is always going to take the path of least resistance towards a wetland, a brook, creek, river, lake, etc. And those water courses, or that the path that it's taking is known as a water course. Let's dive into water courses real quick here. All of the water within a watershed flows towards one primary water course, unless it has been diverted by a constructed water course, such as a canal or an aqueduct. All of that water is going to flow into some sort of river, creek, brook, and it is going to travel towards an endpoint, which down here in Southern California is typically the ocean. All right. So these flows, they can flow continuously, occasionally, or intermittently. in these streams. You want to pay attention to this next part or memorize it, remember it somehow because you will see questions regarding these different types of streams in some upcoming quizzes and midterm final, etc. So water that flows continuously all the time throughout the year is known as a perennial stream. Water that only flows occasionally during and shortly after a rainstorm would be considered an ephemeral stream. And then you have intermittent streams, which is when the groundwater levels are high and that water just travels through those streams, even when during dry times. All right, so let's talk about storage created by dams. This would be considered a natural storage, as the water is still considered an open source. It's not in a constructed reservoir. So, most lakes in the world are actually occurring in glaciated regions, areas where it snows or ice is created due to the freezing conditions. And then as it warms up, it creates these lakes. So small lakes formed by receding glaciers are also called pedals. So you might want to remember that. You might see that on a quiz. Impoundments would be man-made lakes. They're usually built somewhere where damming a valley or stream or river can form a reservoir. So if you've noticed, most at the end of most rivers or streams, you're going to find a lake. And then at the other end of that, you're going to find that dam. So off-stream reservoirs constructed, and those are just where you don't want to impact the flow of that river, but you still need dam for water storage. So that would be considered an off-stream reservoir. There are four different types of dams. You've got the arch type dam, you've got a buttress type, and you got an embankment type, and a gravity type. Um, The materials used to construct these are listed here. This right here is a cross-sectional view, meaning that if you were looking at it from the side, if you could cut open into the mountain and look, or whatever it is that's damming it up, and look at it from the side, you'd see here's your water level, and then this is how that dam is constructed. The plan view would be a top-down view. So when you're looking at these, just to give you an idea of how these images are put together. But that's how the four different types of dams are constructed and what they're made of and how they look. Dam intakes. Right here you can see you've got multiple levels of intakes. The reason you would want that is because the water quality can vary at these different levels in the lake. Or as you draw down the water in the lake, you want to be able to have these other intakes to be able to continuously draw water and send it on down into the system. So we're going to briefly talk about photosynthesis and its effect on water quality. Photosynthesis is the biological process by which green plants, algae, and some other bacteria convert light energy into chemical energy stored in glucose. It is essential for life on Earth as it produces oxygen and forms the basis of our food chain. So, continuing on here. So, dissolved oxygen. Typically, you're going to find more oxygen near the surface of the water. And then as you go deeper, you're going to find less and less oxygen. Like I said here, plants and aquatic life need varying amounts of oxygen to survive. So here's just a quick little graph of what types of animals, need to stay at what levels of the water in order to get enough oxygen to survive. Lake stratification, otherwise known as thermal stratification, would be the temperature of the water at different levels. So the warmer the water is, it would be the epsilon level, and then on down to the hypolimnion level. You could see over here, in this range here, water temperature is fairly warm. It's in degrees Celsius, so it's Right here, it's probably around 80 degrees, and then it drops off as it uh, gets on down to closer to about, 10 degrees Celsius, and then on down to 4 degrees Celsius, not quite freezing. But these would be the temperature ranges of any body of water. So the reason we talk about thermal stratification is because it can lead to what's known as lake turnover. Uh, During lake turnover, what you have is you have this uh, colder source of water on top that is frozen with a warmer source down here. As you can see, you're about 0 degrees Celsius down to 4 degrees Celsius. However, once this level melts off, you get this turnover, and that warmer water is going to want to come up to the top or on the surface. And one of the issues that you can really have is that it will disrupt aquatic life and cause odor issues. So a lot of times if you're driving past a water source and you start to smell something during the springtime, it could be due to, or the autumn time, it could be due to that lake turnover. What's happening is it's confusing a lot of the aquatic life that we had talked about on the previous slide, and it's thinking it needs to be down deeper or it needs to be up higher, depending on what animal it was, and it can cause them to die off. Stream contamination. All right. So obviously, every stream is at the mercy of all upstream users. There's been plenty of instances in the history of America where people have discharged all kinds of contaminants, waste into a watershed, thinking, hey, it's no longer my problem. However, there are plenty of laws and regulations that will bring that back to their front step and make it their problem. So you got spills of industrial waste or from barges. You have industrial leaks, animal waste, and any kind of heavy spring runoff. Especially down here in Southern California where it doesn't rain a whole lot. A lot of you have noticed, I'm sure, that when we do finally get some rain, you start to see all the oil that the vehicles are putting out on the road, and it makes it for a slick condition. Lake contamination, that could be from multiple different sources. Lakes and reservoirs obviously are vulnerable to natural and human contamination. You will find high nitrate levels, not nitrite. Of course, heavy sedimentation, excessive algae growth. Something that happens down here in Southern California is that we typically have algae blooms in the month of October, which, the treatment plants then have to use a different treatment technique, which can affect the taste and odor of our water. Zebra and quagga mussels are a big issue. Those have been around since the 80s, and once you got them, you typically never get rid of them. But they're an invasive species of mussels that spread quickly and attach onto everything, and they eat up aquatic life. They tend to kill off a lot of aquatic life once they infiltrate those areas. And then again, lake stratification, which can be considered contamination if you've got a bunch of aquatic life that is dying. So, surface waters, water quality. So, typically, you're going to find that you have excessive turbidity. It is obviously susceptible to microbiological contamination, susceptible to chemical or radiological contamination. Most rocks and soils have radon or some kind of radiological contamination that they put out. Um, just FYI. Obviously, you're going to have taste and odor and color issues, and then like I said, another contamination is the occurrence of algae growth, and then the water temperature itself is going to fluctuate quite heavily. So, continuing on, other factors that contribute to surface water's water quality, it is possible to treat just about any poor water quality condition. The issue then becomes, is it economically sound to do so? Sure, we could treat it, but it's going to cost you. So that's why you have these differences between like maximum contaminant levels and then maximum contaminant level goals. It is a goal to try and get to, but is it economically practical? So it may be more cost effective in some areas where you have poor water quality to just pipe in good water quality to them rather than having to construct some kind of treatment facility and then pipe it just a short distance. Um, there's a lot of overhead and maintenance and ongoing work that happens with the treatment plant, whereas you can have more of a passive system where there isn't all of that overhead and isn't all this maintenance that has to continue on by just piping in the water, the good water source to a remote area or an area where there is a source, but it's not economically feasible to treat it. So, another source of drinking water would be groundwater. Uh, these are some of the characteristics. Constant composition. Typically, your minerals that you're going to find are relatively consistent. You are going to have high mineral content, obviously, because you're pulling water from deep from in the ground and up to the surface that has just been sitting in the Earth's soil. Typically low turbidity, low color, low or no dissolved oxygen. That is a real common occurrence in groundwater. You are going to have high hardness, though. High hardness would be considered, high levels of calcium and magnesium. We'll talk about that in a sec. You have high iron and manganese as well. And then this source is typically for a rural area. A lot of times, like if you can't get, if you can't pipe or construct some kind of aqueduct to take water to these rural areas, groundwater is definitely a viable source, and it's typically enough source to supply everyone in these small rural areas. And again, you are going to have taste and odor issues that will be mostly inorganic in nature. Groundwater, also known as underground reservoirs, are everywhere. And it's the result of infiltration and percolation of water down to the water table through soil and cracks in the consolidated rocks. So, in most areas, you have about 95% of rural populations are served by these groundwater sources. Um, If the water from a well is free of contamination, it will usually stay that way until we screw it up. Some of the ways we could screw it up would be like a gas station, one of their tanks that develops a leak and can seep into a nearby uh, groundwater reservoir and screw it up for basically the next few generations. Uh, you might see this definition or this question pop up. What is a deep well? It's any well that penetrates an impervious layer. So part of groundwater sources is its permeability, and that is how water flows through the soil. You can see here permeability is a measure of a soil's ability to permit water to flow through its pores or voids. Here are a couple examples, just, they say it's an actual path, but I'm sure you've got other paths here, but, water will travel through here. And that's also what is helping to eliminate some of the contaminants on it. Different types of soil are going to allow for different flow rates. So, like sand and gravel will have a higher rate, but you get over to clay and you're going to find that it's really slow. Let's dive into some aquifers. Um, you've got a couple different kinds. You've got a confined aquifer, which is aquifer that has a solid rock formation above and below it. And then you've got an unconfined aquifer, which has a solid rock formation below it, but not necessarily above it. And then you've got a perched aquifer, which is one that just sits above the unconfined aquifer. In addition to that, you've got different types of wells. You've got artesian wells, a water table. So the artesian well is pulling water from the confined aquifer. The water table well would be pulling water from an unconfined aquifer, and then a perched water table well, which is just pulling water from that perched aquifer. The flowing artesian well is due to the fact that the water table sits above where that discharge point is in the well, the artesian well, and that's why it would be a flowing one. One of the things you'll notice here too is that much like a hydraulic gradient, this potentiometric surface drops off the further it gets away from that water table recharge area. And that is common even out in your water distribution system. Here it is called a potentiometric surface, but in like an urban area, you're going to refer to it as a hydraulic grade line. And here we have it's the same thing, just a different graphic to, help get the point across. You have, artesian wells, which are flowing and non-flowing, and then you got the piezometric surface, the height to which water will rise in wells located in an artesian aquifer. So the height. So how do we get that water out of the ground? Well, in the old days, you had wells, and then we advanced those wells, to something more modern. Right? So wells are the most common means of accessing groundwater, and obviously we've come a long ways, from how your parents had to access these things. So one of the most important parts of a well would be considered the sanitary seal, and that is installed at the top of the well casing to prevent the entrance of water, insects, and animals. Last thing you want is one of those going down into your well and contaminating your well water source. You have some openings on it, and that is for the discharge pipe, air vents, any kind of pump control. All right, moving on to casings. To the left here, you can see we've got a typical well casing diagram. You've got the different types of casings here, the conductor, the surface, the intermediate, and the production casing. And in between each of those casings, you're going to want to grout them with cement. Um, as we say here, the areas between the walls of the well casing must be cemented or grouted, and the reason being is that you want to prevent surface water pollution from contaminating the water being drawn. And then the second purpose would be to prevent it from corroding and collapsing. Another major component of a well would be the screen. You want to make sure that these are properly sized to allow the maximum amount of water to enter the well while blocking formation of materials from entering. If you get materials to enter in, it could damage your pumps, so that is quite important. There are four different types of screens. You've got slotted, wound, bridged, and louvered. And then depending on you know, the soil type, the corrosivity, and the cleaning of these screens will determine which type of screen that you're going to want to select for your purposes. Just to touch on well grouting again, you will see this on some kind of quiz or exam in the future. But they are well grouting seals the well from possible pollution, protects the casing against exterior corrosion, and then prevents collapsing or assists in the prevention of collapsing of your well hole. It's typically going to be cement or bentonite that is used for the grouting. And then, of course, you're filling from the bottom up. I don't know how else you would fill this. I don't believe you can fill well casing from the top down. Just gravity wouldn't allow that. But you want to make sure that you're getting rid of any kind of air gaps. You don't want voids in there because those are weak points and will lead to failure. Moving on to development. Development is there's many different methods to do it, but ultimately what you're trying to achieve is the maximum well yield from your well. So every single new well should be uh, should go through the step of development before being put into production, just to achieve that maximum yield. All right, so you've got your pump that sits up on the top. You've got, your surface here. So then you've got your radius of influence, and that is all the way out to how far that pump can reach in this groundwater source. You've got your static water level, which is the water level below the ground, the top of your groundwater level. And then the cone of depression would be considered this cone that is developed when the pump is in operation. Your drawdown is the water level from a static water level down to a pumping level. And of course, you got your screens down here at the bottom where the water's coming in, coming up, the water's coming up, and then being discharged out. So, when talking about groundwater, there's a couple different formulas that you're going to become real familiar with if you haven't already. You've got well yield and then specific capacity. Well yield would be how much gallons per minute your well can produce, while as the specific capacity would be the performance of that well based on the uh, gallons per minute per feet of drawdown. This slide here is a nice graphical representation and a descriptive example of drawdown and how to calculate that out. Uh, it's slide number 34. If you want to come back to this one, you will have a problem or two on your homework with calculating drawdown. So here's just a nice example of how to calculate it out. Feel free to reference this one. Okay, here I've got just a couple of quick specific capacity questions, just examples to help you when you go to do your homework. So, if you have a well yield of 2,500 gallons per minute and the drawdown is measured at 75 feet, what is the specific capacity? Well, to do this, you're going to need to divide gallons per minute by feet. So, in this case, it would be 2,500 gallons per minute divided by 75 feet. And when you calculate that out, you get a specific capacity of 33.3 gallons per minute per foot. Be sure to make sure that your units of measurement are correct anytime you're doing any kind of math problem, really. So let's do another one real quick. It, it's basically the same thing. It's just taking different numbers and plugging them into the correct spot so that way you can get the answer. So here you'll see you've got, 1,575 gallons per minute and you're dividing it by 25. So that's going to give you 63 gallons per minute per foot. All right, let's dive into some groundwater mathematics here. In this problem, we are going to solve for specific capacity. However, some of the other information that is given to you in other questions has not been given to you, so you got to solve for that as well. So let's dive into this one. It's determine the specific capacity of a well utilized during a 12-hour period that filled a 60-foot diameter tank to a height of 20 feet. The static level of the groundwater is at 45 feet below grade, and after 12 hours, the pumping level was at 73 feet below grade. So we are trying to solve for the flow, but we need to know what the volume is. And do we know what that is yet? Not yet. So let's solve for that. So you're going to solve for the volume of a reservoir, which is something at this point you should be pretty comfortable doing. But for those of you who just need a little refresher in case you haven't had this kind of math in a while, I'll give you the formulas and you can plug and play and solve these problems. All right, so diameter times 0.785 times height times 7.48 is going to give us, well, you plug in the numbers, so 60 times 60 times 0.75 times 20 times 7.48 is going to give you 422,770 gallons. So we want to take that number and plug it into the next formula. Let's see here. Here we go. So now we have volume. So we know that we're going to plug that in here up at the top. So that 422,770 gallons gets plugged in there. And then we knew that it was a 12-hour period during that pumping time. So that 12 hours goes onto the bottom. However, We do things in minutes, not hours. So we need to convert that 12 hours into minutes. So that's why you're going to go 12 times 60, and that is going to give you 587 gallons per minute. But we're not done there. We've only solved part of the problem. Next, so now we have basically the well yield, right? That's all we have solved for at this point. So you're going to plug in that number up at the top there and get that 587 gallons per minute. And then we have to solve for the drawdown. And as you can see in the question, it gives you that information there. So 73 minus 45 equals 28. And if you punch in that into your calculator, you're going to wind up with 21 gallons per minute per foot for specific capacity. And that's how you solve that. So, groundwater contamination. Let's move on to some of this real quick. Um, your new wells, you want those to be located a safe distance from sources of potential contamination. That seems like an obvious statement. However, um, people don't always pay attention to their surroundings, let's just say. So, contamination can usually come in the form of a human activity or a natural occurrence again. So potential sources for contamination could be landfills, industrial waste, septic tanks, deep wells, de-icing activities, like around airports. There's a whole bunch of different ways to contaminate your groundwater source. So this list is not all encompassing. It's just a good list to give you an idea. All right, groundwater contamination continued. On the left there is a nice little diagram of how aquifers or groundwaters can be contaminated from different sources, but then other ways described on the right here. Um, so going into that, you can overpump your well, which would allow for intrusion of like ocean waters or surface waters, and then you have the resulting radon, like I described earlier, which is naturally occurring in your soils, pushing out gamma, alpha, beta rays out into the water. I see, we've got asbestos listed there, but as a fun fact, the state rock of California is a rock called serpentine. And some forms of that serpentine contain what's called chrysotile, which is actually a form of asbestos. And, as many of you know, asbestos is cancer causing. So the state rock of California, is bad for you. Anyway, moving on. New wells can contaminate existing ones because of the sources that were not anticipated, like taste and odor. And then you've got natural, synthetic, organic, or inorganic means of contaminating any water source, or excuse me, any groundwater. Just when you thought that there couldn't be any more groundwater math, here we go. Let's have some more groundwater math. All right. Uh, you won't see too many of these problems, but I have seen it on my distribution exam, so I thought I'd share it with you. So, well blending math, right? Well, blending math. So, all right, let's dive into this problem, right? What is the resulting concentration of arsenic if a well contains 50 parts per billion? Well B contains 10 parts per billion. Well C has 2 parts per billion, and all are pumping at the same flow rate. Well, let's throw that into a nice little question here, and we'll pump out a formula for you. All right. Well A in parts per billion plus well B in parts per billion plus well C divided by the number of pumps you have. So like I said before, in the problem, they're all flowing at the same rate. So now we just need to determine the number of pumps. And when you put 50 plus 10 plus 2, you get 62 divided by 3. That gives you, well, there's a rounding error there. Yeah, it's rounded up to 21 parts per billion. Um, but that's a quick and easy formula for you. However, that's not always going to be the case. typically your wells are going to pump at different levels or gallons per minute. So that's why we have this problem. So we can do more fun math. All right, so what is the resulting concentration of arsenic if a well contains 50 parts per, if well A contains 50 parts per billion at 800 gallons per minute? Well B has 10 parts per billion at 500 gallons per minute, and well C has 2 parts per million at 300 gallons per minute. All right, punch that into a formula. All right, your formula is going to look like this. Well A flow times the parts per billion, and then the same for wells B and C, and then those would be added and then divided by the total production or gallons per minute. So you've got 800 times 50, 500 times 10, 300 times 2 divided by 1600 gallons per minute. All right, so you run those numbers, calculate it out, and eventually you're going to get to 28.5 parts per billion. And again, what we were trying to solve was for the resulting concentration of arsenic, from the three wells. So you'll probably see that question on a quiz sometime in the future. All right, so moving on from ground, well, we're still talking about groundwater. However, we're talking about water characteristics. Hard water, something that we definitely have here in Southern California. Hard water is a combination of both calcium and magnesium ions. And in the diagram to the lower right, you could see a little map of where hard water exists throughout, or the hard water levels generally throughout the United States, or the continental United States. You also have iron and manganese, which is a discoloration of water and has the potential to stain your water fixtures. Yeah, I wouldn't drink that. How do you treat for these groundwater conditions? Well, it's known as in situ treatment, and which is the treatment of that raw water source. Typically, you're going to inject what's called potassium permanganate, and it actually does turn purple. So when you see that purple on there, that is the actual color that the chemicals create. But what do they do? They oxidize the dissolved iron, manganese, and hydrogen sulfide into solid particles, and then they are pumped out of the groundwater and removed. And so that's one method of treating groundwater. So, moving on, we're going to discuss the emergency and alternative water sources. We'll briefly go over the causes. What are some of the alternative water sources, which could be like an interconnection system, emergency provisions like a truck, and then water reuse, known as indirect and direct water reuse. So, why would you need alternative or emergency water sources? Many different reasons. It could be just a scheduled shutdown, an emergency shutdown, where the water authority or your water purveyor is going offline on a major pipeline. Typically, you're required to have a 10-day storage to get you by, and that I believe is required by the ISO. So obviously, things you need to be concerned with, obviously, are public health would be your primary reason. But then anytime you have a loss of system pressure is an opportunity for some kind of contamination into your system, especially even with pipes that have been installed in the grounds. So you have a couple different categories or causes. Like I said, natural disasters could be one. A lot of you probably remember that earthquake that took place on Easter Sunday, which created a bunch of um, water quality issues and problems, especially down south. Another one, obviously, all over the world, you're experiencing these earthquakes, floods, hurricanes, tornadoes, etc. These all can create emergency situations for any kind of water system. And then you got human activity. Unfortunately, this does happen. You've got vandalism, explosions, strikes, etc., terrorism. These are all real things that still happen and affect the public at large. One of the things that has been put in place since 2018 is called the America's Water Infrastructure Act, which is ways that we go through when we look at the risk and resiliency of every single distribution system out there. And then after evaluating the risk resiliency assessment, you do what's called a ERP, an emergency response plan. So that is actually a requirement of every water purveyor in the country. And then you got indirect human activity. That can mean equipment failure, such as a backflow device that fails and water is sent out into the distribution system, or it could be a breakdown caused by human error. All right, so some alternative sources. You definitely want to have more than one intake for your reservoirs at dams, like we discussed earlier. You saw how there was intakes at different elevations. So if you have contamination or water quality issues, you can always, you know, pull from a different intake to continue to provide yourself with the needed water. And then you can always, have wells that are constructed to replenish those surface water sources. Groundwater systems, obviously, you want to have enough wells to meet the demand of the public, but then you want those to be located in different aquifers. So if one is contaminated, then you can continue to pull from the other while you try to do some kind of in situ treatment. Um, you might be able to get away with having multiple wells on the same aquifer just so long as they're far enough apart that one won't affect the other. Right. Inter system connections. These are really common. Everyone, wants to be good stewards and neighbors with other member agencies. And that's why you have these inter-system connections. And it's a way of, taking water from your neighbor to help supplement you during times of need. It's most common in urban and suburban areas, and it's definitely an emergency source should you need it. I, working at VID, I know that, we have multiple interconnections with our neighbors, whether it be Carlsbad, Vallecillos, Rincon del Diablo, where they are, we have these connections set up. So if there is a fire emergency and they're pulling from their fire hydrants, their water pressure may not necessarily meet the proper demands set by the ISO. And so our regulators would open up and help feed their system in those times. Um, but they're typically, emergency connections. You can have them set up where you're just connecting two pipes from a fire hose, or you can have it where there is temporary piping that's installed along with a meter to feed those different systems. And then you have something that's permanently installed, which would consist of pipes, meters, some kind of pressure reducing valve or a booster pump. And obviously, you want sampling ports because you want to make sure that the water that you're providing or receiving meets water quality standard minimums. Emergency provisions here, we're getting into, like issues like the city of Poway had several years ago when they had they contaminated their main source and everyone was drinking from bottled waters, or you can have some kind of a tank truck. Um, so some of the issues that you have though with bottled water is that you can only provide so much, and it really is a bad perception from the public. One of the things though with bottled water is that there is no taste and odor or regulatory compliance when it comes to bottled water. So the only thing that's regulated is the public system, not the private. I mean, they do have their own regulations, but they're not held to the same standards that your public distribution system is. So you do have tank trucks, which are great. You know, they can hold a lot of water, but they do require adequate disinfection. And then if things get bad enough, you have water rationing, which, you know, anyone who's lived in Southern California long enough is probably gone through one of these drought conditions where you're only allowed to water your lawn on certain days. So those are some of the things that can take place during an emergency. Water reuse. You got two different types. You've got indirect and direct. Indirect would be considered the use of water from streams that have some kind of a discharge happening upstream, but that's been treated through a natural process. Um, there's actually millions of people who consume water from this type of indirect reuse. However, there needs to be adequate communication between, you know, who's discharging and, you know, receiving that, so that way they can make sure that they have adequate treatment in place to handle their discharge. And then there's the direct reuse, which is not something that you want to drink. This is typically going to be water that's used for reclaim, irrigation, non-potable sources. It can have some kind of waste added to it. So anytime you see any kind of direct reuse, yeah, you definitely want to make sure you're not consuming any of that. Diving into it here, yeah, so like I said before, indirect reuse is definitely it occurs in every major system, river system in the United States, and there's usually a treatment method such as reverse osmosis, which happens to be the most common. For those of you who don't know, reverse osmosis is the method of using high pressure water forced across semi-permeable membranes to produce nearly pure water. The Carlsbad desal plant is probably the most local um, desal source that we have, or indirect reuse source that we have here in Southern California. Continuing on with that indirect reuse, one method is desalination, and that is the method of turning seawater into fresh water. Typically, the method will be reverse osmosis. That's just the most common method. It's in incredible way of just removing all the impurities in the water and having a nice fresh source at the end of it. Uh, Distillation and evaporation are another indirect reuse method. When I served in the Navy, I worked down the engine room, and we had evaporators that would provide water, fresh water to the ship. But the way it would do that is it would take that water in, heat it up, flash it to steam, and then all your water would fall, whereas the, you know, gases and, you know, impurities would separate from that water, and you would send it through multiple stages of that to make that water nice and pure and fresh for drinking. The only issue is that you can't produce that much on a daily basis. So it's very important to have a multiple barrier system though, with the indirect reuse, because you don't want your public getting sick. So it's important that it goes through all of these stages prior to going out into a public system or being provided to the public. So you want to make sure it has some kind of primary and secondary treatment, whether that be dual media filtration, chemical additions, disinfection. And then you also want a pre-treatment prior to the reverse osmosis system. Um, if you're not treating that water and just sending it to the reverse osmosis system, you're going to go through those membrane filters quite fast, and those are quite expensive. Um, so it's really important that every single step here works and not one of them fails. Otherwise, you can't provide that water to the public. All right, desal. Um, Huge advantage. I mean, obviously, most of the world is made up of ocean water. And so being able to draw from that source is really important. Um, the water quality can be great, and it's a reliable source. You know, there's tons of it. However, the disadvantages to it are also uh, just as important to consider. Obviously, the cost of that water is going to be very expensive versus conventional methods. The recovery, so here we're talking like if you were to take in 100 gallons, you're only going to be able to get 15 to 50 gallons of output. Um, and then obviously the rest of that water, has to be discharged back out into the ocean. And so that's that potential for coastal zone impacts. Plus, these plants have to be built, relatively close to the ocean or to the coastline, which is unsightly in and of itself. And then lastly, there's a lot of energy use that goes along with it. So, like always, if you got questions, please feel free to email me or reach out to me in some way, and I'll do what I can to help you out. All right, till next time.